Okay. So, yesterday we talked about finding the mean and the standard deviation from the table, right? And then we talked about unusual values. In the same ones that are on your formula sheet that will give you the mean and the standard deviation of a binomial. Okay? So, the biggest piece is going to be recognizing this as binomial. These are the formulas I want to use. Okay. So, in this particular case, we take a random sample of 15 students, so we still have n equals 15, p equals 0.4. If I ask you what is the mean, you're going to say 15 times 0.4. This is equivalent to if you typed it in that typed in the whole table. This is a way better way, way faster way to get there. Okay? The standard deviation will be the square root of 15 times 0.4 times Q is that probability of failure. And I got it to be 1.90. Everybody good? Okay. Lastly, would it be unusual? Just like binomials are a type of random variable. What did we say yesterday about unusual? More than two standard deviations from the mean. So some of you do 6 minus 2 times 1.9. Some of you do 6 plus 2 times 1.9. So we can say, what is 2 standard deviations? 9.8? Okay. So would it be unusual to get one business major? Yeah. So one is unusual. What about 8? 14? Everybody good? Cool. Hey, real quick reminder. What's going on tomorrow? We're going to do the Poisson distribution. We'll probably have a little bit of time towards the end, I would think. But you've got homework due by midnight, Excel lab due by midnight.
The homework is what you gave us like a while ago, isn't it?
The homework is online.
Yeah.
And they're both due tomorrow by midnight. I'm available before school, and all you get, like, my availability is always there to help you with it if you're coming across questions you don't know how to do. Okay?
I have a binder, just don't know.
Today we're going to talk about a different discrete probability distribution. This one is called the Poisson distribution. So we're getting to the stage where what you guys are going to be doing frequently is, like, we're learning lots and lots of different probability tools. So one of the things that we need to start thinking through is, when do we use what? Okay, so yesterday we learned about binomial probabilities, and those are happen when we have repeated trials and we're finding the number of successes, the probability of a certain amount of successes. Okay? The Poisson distribution is all about, like, how often does something happen over a specified interval. So specifically, you're likely to get a time interval. So we've been using a bunch of different examples of what are probability events that are different from the classic spinning a spinner, rolling a die. And one of the ones I've given you guys is that, the first hour that a store is open, how many customers does it get? That would be an example of a Poisson variable. Is everybody good? Okay. So, you guys, if I have the number of occurrences something happens, Can you get 7.2 occurrences happen on any given day? No, it's still this idea of this thing happens or it doesn't. Is everybody good? Okay. So X is going to be the variable, the unknown is the number of times and something occurs. And in order for something to be distributed according to the Poisson distribution is that each occurrence needs to be random, each occurrence needs to be independent, and they need to be uniformly distributed over the interval. And here's what I mean. If I say, oh, at this store, we get an average of 10 people in the first hour, okay? That means that in the first 5 minutes, and the second 5 minutes, and the third 5 minutes, they're all like equally likely to have people in them. Is everybody good? Okay. Now, you will be, the Poisson distribution is going to be described like, just as I said, on average, you get 10 people an hour in that 1 hour. So, you're going to be given the average, and the mean of the Poisson distribution is the average. Is everybody good? The standard deviation is usually the square root of that average. So let's look at some examples. All right. So, Unit 4 homework / lab due by midnight tonight. We will finish probably about halfway through the class period today, and we will finish Unit 5. So, Unit 5 lab will be block day next week. Okay? I have not done my advanced version of it yet, so I don't know if it'll take the whole block day or not. So don't think, oh, she gave us a block day, it must take a long time. I'm giving you a block day because that's where it falls. Okay? With late start on Monday we're going to do a short lesson. So it's not going to be a free day or a work day. There'll be a very, very short lesson on normal distributions on Monday, lab on Tuesday. Okay, the Unit 5 lab and homework are due on Thursday at midnight. So the reason I'm pointing this out is that we will finish Unit 5 today. It wouldn't be the worst idea for you to start at least the homework outside of class over the weekend. That's why I'm pointing this out, okay, guys? Because there won't be a ton of class time to work on homework. So the weekend might be a decent time to try. You know, if you're bored on Sunday night, it's not like there's a game or anything anybody's going to be watching, right? You guys, the Super Bowl is on Sunday. For those of you who aren't football fans, the Super Bowl is on Sunday. Everybody good? In terms of, like, logistics, after this, you remember at the beginning of the semester, you got a sheet with the due date of every assignment? We will be caught up from the snow days after this assignment. So those due dates, the due dates for Unit 4 and Unit 5 were not accurate. The due dates for Unit 6, the due dates for Unit 6 are. Did you guys get what I'm saying there? Okay, great. So, when we say the mean number of tardies of Grandview students in a 5-day week is 58.8. Okay, again, if this is distributed Poissonly, we would expect the same number of tardies on Mondays as Tuesdays, as Wednesdays, as Thursdays. Everybody good? All right. What would the mean and the standard deviation be if we measured these in tardies per day? How would we do this?
You divide by 5.
For the mean, we would take that 58.8 and divide by 5. I believe it works out to be about 11.76. For the standard deviation, all we have to do is the square root of that 11.76 for this distribution. So different setting, different scenario, different set of rules. Both sets of rules are right here on your formula sheet. You have them, okay? So I don't need you to memorize what are the mean and the standard deviation, just how to apply them, okay? Let's see, I would imagine this is like somewhere between 2 and 3. No, between 3 and 4. Like 3.43? Is that, we all good? Okay. All right. So, would it be unusual for there to be 15 tardies? How did we measure unusual? More than 2 standard deviations. So, we have to decide, is 15 more than 2 standard deviations above our mean? So, I would expect to see not just a yes or no. This is something that came up on the last test, y'all, where there were questions that were yes or no with no mathematical support. The expectation is always mathematical support. So, the 15 is not greater than 18.62, not unusual. I'd expect to see something kind of like that. All right. Find the probability there are exactly 10 tardies in a day. Okay, so you guys, yesterday we did, when we had to find the probability that x was equal to 10, we chose binom PDF. Yes, PDF gave us exactly. Okay, should we choose binom PDF here? No, because this is not binomial. Is everybody with me? But go back to where you found that binom PDF. So go second distribution and bring up the distribution menu. So second vars. And if you scroll, I bet you might find something that might help you with the Poisson distribution. In fact, you might see Poisson PDF. So when the distribution is a Poisson distribution, you use Poisson. When the distribution is binomial, you pick binom. Is everybody good? So if I do Poisson PDF, it's got this fancy symbol here, which is the Greek lambda. You guys, it just wants to know what is the mean. What did we say our mean was? 11.76. And I know this because this was 10 tardies in a day. If this had said 10 tardies in a week, is everybody good? And so, for lambda, you're going to put that 11.76. For your x value, you'll hit paste. You guys, I got 0.109. Everybody good? All right. Now, just to give you some perspective, remember we've been talking about really what's going on is it possible there's on a day that there are 0 tardies? And then we could find the probability that there are 0 tardies, yes? And then we could probably find the probability of 1 tardy, et cetera, et cetera. I'm going to do a little. All right, so what we just found was the probability of getting exactly 10. Is everybody okay? All right, now, what is the probability that more than 15 tardies occurred in a day? How would I put that in symbols? X is not greater than or equal to. More than would be strictly more than. Is everybody with me? More than 15. Okay. So again, I'm going to envision, what does this table look like? So if I'm asking what is the probability of more than 15, are you guys with me? I'm trying to find this side. All of those probabilities. This CDF does less than or equal to. So I'm going to do 1 minus the probability X is less than or equal to. So what are all the other probabilities? In other words, what is my red shaded? Less than or equal to? 15. So we're doing 1 minus the probability X is less than or equal to 15. You guys, this is a tough concept, okay? Because there's a lot of moving parts to it. I'm going to teach you a different set of questioning. Is that a little bit? I'll keep it. Thank you. Okay. You guys, which outcomes are greater than 15? If I asked you to start listing them, greater than 15, 16, 17, 18. So which ones are not? 15, 14, 13. So we're subtracting the not greater than 15. Okay. Another way of thinking about it is you have that boundary point. The 15, this 15 needs to be included exactly once. If I say strictly greater, am I including the 15 here? No. Then I need to include it here. Everybody good? Okay. Now, how many tardies are we expecting in a day? 11.76 tardies is what we would expect on average per day, right? So, more than 15, do you think that's going to be a big probability or a small probability? I would think it would be kind of small. Are we all on the same page? I did 1 minus poisson CDF. And then for the mean, I put 11.76, and for the X value, I put 15. Do we have any questions? All right. All right. On average, 20 calls are received at a customer service center between 9 and 10. Okay, as I look at this, the minute I see this, I see a range of times. Okay, the minute I see that range of times, that is my cue that I need to pick Poisson. Okay. So when I say what is the distribution, you guys, whenever I say what is the distribution, I want you to say the name and then what are the important features. And for Poisson, the important feature is the mean. And if I asked you what the standard deviation of this is, what would you say? The square root of 20. 4.47. Great. All right, what is the probability that the center gets fewer than 14? How do I write fewer than 14? Strictly less than. Can I type it into the calculator like this? Okay, according to the call center, right? If they say fewer than 14, which outcomes is that? 13, 12, 10. So that's really the probability X is less than or equal to 13. And now how do I find this answer? Poisson CDF. You guys, should this be a big or a small probability? We would expect it to happen 20 times. 13 feels kind of small, yeah. Are we in agreement?
What exactly you typing in your calculator?
So I choose Poisson CDF.
Yeah.
When it asks me this symbol,
Mm-hmm.
they want the mean.
Okay.
So the mean in this case would be 20. And then my x value would be 14. Everybody good? All right. What is the probability of getting exactly 22 calls? Now, before you do anything, is this going to be high or low? High?
Medium.
It averages 20.
It's within the standard deviation.
Okay. I'm with you. I'm totally with you. This will be interesting. Let's see. Yeah? Because this might be lower than we expected, right? What is the probability x equals 20? Like, what is the probability we get exactly our mean?
Not much higher than that.
Not that high.
Yeah.
But if we said, well, what's the probability between so any one specific outcome does not need to have a high probability. And by the way, x equals 20 is the most likely. Okay? And so singular outcomes might not have that probability, not have that high of a probability because, well, there's still lots of opportunity there, right? There's lots of different possible outcomes. So even though one can be the most frequent, doesn't make it likely. Everybody good? All right. What's the probability that the center gets at least 24 calls between 9 and 9:30?
Will we divide the mean in half?
Okay, so we're dealing with half the time, and if we're using Poisson, we're assuming that you get that between 9 and 9:30 is the same as between 9:30 and 10, like any interval is about the same. Okay? So in this case, what we would have to do to find that mean is we would take the original mean and cut it in half. So my mean is 10, and then we're finding the probability that my number of calls is greater than or equal to 24. And using your gut instinct, should this be a high probability or a low probability?
No.
Very low.
Very low, right? You're expecting 10. You're not going to get 24. Like, we should expect a very low probability. Now, in terms of your calculator, which outcomes are greater than or equal to 24? 24. 24 is greater than or equal to, right? So 24, 25, 26. So in this case, we can only do less than, so I'm going to do 1 minus. The probability x is less than or equal to. So which outcomes weren't greater than or equal to 24? 23, 22, 21.
1 minus that number, right?
And so this feels like it takes you have to do a little bit of like kind of finesse and thinking through your reasoning for each amount. and if I'm remembering correctly, it's like 0.00012, or your calculator says 1.2 times 10 to the negative fourth. Guys, when your calculator gives you the answer in scientific notation, I'm very comfortable with accepting scientific notation. Can I tell you what answer I will not accept?
E to the negative.
1.2. Why should I not accept 1.2?
It goes against the rules.
Because probability can't be bigger than 1. Okay, that tells me that you're just plugging and chugging the calculator, not really understanding what's going on. Yeah?
So when do you have to exactly change the, like how we can't plug in x is greater than or equal to 24. When do we have to flip the signs? When it, like the calculator doesn't accept when x is,
The calculator can only do less than or equal to.
okay.
Okay, so when it was strictly less than, turning a less than into a less, well, turning a less than into a less than or equal to is not that bad.
Yeah.
So when do you do the 1 minus is because when you need to,
Yeah.
right? So whenever there's a greater than, in some capacity, you're going to have to do that 1 minus.
Yeah, so you have to kind of change it when it's less than, when x is less than or equal to a number?
No, if you're finding the probability x is less than or equal to something, the CDF can do it.
Yeah, that's what I meant to say, sorry. That's
Yeah,
what I
yeah,
meant to
yeah.
say.
Okay? All right, I just want to point out one more thing. You guys, when it was strictly greater than 15, was the 15 included here? Greater than 15? Was the 15 included in the greater than 15? No. So I had to have less than or equal to that 15 here. Was the 24 included here? So I had to take this down by 1, so I didn't include it here. It has to be included exactly once. All right, last problem, and then we're done. What is the probability the center gets at most 11 calls between 9:15 and 9:30? You guys, what's my mean between 9:15 and 9:30? 5. Because that's 1/4 of my original window, so I have to do 20 divided by 5. And so if I'm expecting 5 calls, what would at most mean? Less than or equal to 11. So should we, if I'm expecting 5, should I expect a high probability here or a low probability here? A really high. Like if I'm expecting 5, I'm probably going to get less than or equal to 11. Is this like, and the reason I'm pointing this out is these are the types of questions where kids forget the 1 minus. Like thinking through intuitively beforehand, what are we expecting to get is not the worst scenario in the world. Okay? So I think we do get like 0.99 or something.
Yeah.
0.995? Okay. Okay. At this point, I am done with this Unit 5. All right. So your test will be over Units 4, 5, and 6. So we're 2/3 of the way through what's going to be on the next test. I would recommend that you are consistently going back and looking at the stuff in Unit 4. That was the stuff on two-way tables, the addition rule, the multiplication rule. Okay? And then Unit 5, this stuff. Unit 6 is going to have a little bit more calculator stuff, and then we'll take the test.
When's the test?
I don't know. I mean, I do. Test number 2. I think I have it on the 24th and the 25th. There's no block days that week.
Why is that?
Oh, ACT. Juniors will chat. Because on the 25th, you're taking the ACT.
That sounds like why.